What is a bonding orbital?
A molecular orbital that is more stable than the atomic orbitals that were combined to generate it.
What is a bonding orbital?
A molecular orbital that is more stable than the atomic orbitals that were combined to generate it.
What is the Boyle's law?
Law stating that the pressure and volume of gas are inversely proportional.
What is the Boyle's law?
Law stating that the pressure and volume of gas are inversely proportional.
What is a buffer?
A solution that tends to resist changes in pH upon addition of an acid or base.
What is a buffer?
A solution that tends to resist changes in pH upon addition of an acid or base.
What is a calorie?
A unit of energy equal to 4.184 joules.
What is a calorie?
A unit of energy equal to 4.184 joules.
What is a calorimeter?
A tool used to measure the heat change associated with a chemical reaction.
What is a calorimeter?
A tool used to measure the heat change associated with a chemical reaction.
Why do hard-boiled egg yolks turn green?
When egg whites cook, a small amount of hydrogen sulfide, H2S, is released from sulfur-containing amino acids like cysteine or methionine. If the H2S migrates to the yolk, it combines with iron atoms to produce ferrous sulfide. FeS, which is a dark-colored material that looks green mixed with the bright yellow yolk. Ferric sulfide, Fe2S3, is also sometimes claimed to be formed in this process. likely because it is itself a yellow-green substance. There is, however, less data to back this up, aside from the convenient color match.
What is a bond strength?
A measure of the energy required to break a chemical bond.
What is a calorimeter?
A tool used to measure the heat change associated with a chemical reaction.
What is an amalgam?
An alloy of mercury.
Why do hard-boiled eggs spin, while raw eggs don't?
Hard-boiled eggs are solid all the way through, so when you spin the egg, all the energy you apply goes into spinning the whole object. Raw eggs have yolks that are free to move about the interior of the egg, however. So when you spin a raw egg, the yolk moves to the outer edge of the inside of the egg, which consumes some of the energy you applied. The other difference you can see is what happens after you stop these two eggs from spinning. Stopping the hard-boiling egg stops the entire system. Because the yolk is trapped in the solid, cooked egg white. Inside the raw egg, however, even after you stop it, the yolk is still spinning around. So if you take your finger off of a raw egg that was just spinning, it can start moving again, seemingly on its own.
What is a calorie?
A unit of energy equal to 4.184 joules.
What is an anion?
A negatively charged ion.
What is amorphous?
A solid without a repeating, ordered structure.
What is a bond order?
Number of pairs of electrons shared by two atoms.
Why is there lime in my tortillas?
First, let's clarify the question. We're talking about traditional corn tortillas. And by lime we're referring to a calcium hydroxide solution, not the green fruit. Corn tortillas were historically made from what is called nixtamalized corn, which involves soaking corn in a basic solution like calcium hydroxide. The process goes back about 3,000 years to the Aztec and Mayan civilizations. Because of its ancient origin, how it was discovered isn't clear, but why it survived is now obvious. Corn lacks one of the essential vitamins required in human diets. It doesn't have niacin, also called vitamin B3. People who don't get enough niacin in their diet develop a disease known as pellagra. Just like if you lack vitamin C, you get scurvy, which has some awful symptoms. Obviously this is a problem if your civilization's staple food is corn. Somehow, the Aztec or Mayan people figured out that cooking corn with strong bases prevented people from getting pellagra. Now we know this is because niacin is not readily available in corn, but can be released by treatment with a strong base.
What is an alpha particle?
A particle consisting of 2 neutrons and 2 protons, i.e., a helium nucleus.
What is the Boyle's law?
Law stating that the pressure and volume of gas are inversely proportional.
What is black body radiation?
Electromagnetic radiation given off by a black body. At room temperature most of this radiation is in the infrared. But at higher temperatures visible light can be emitted.
What's the difference between brown and white eggs?
Besides their color, the only difference is the color of the chicken that laid it. White feathered chickens lay white eggs, brown feathered chickens lay brown eggs. That's it. The inside of the eggs are identical in every way, assuming the chickens you're comparing were on identical diets.
What is an alkali earth metal?
Group 2 of the periodic table, i.e. B, Mg, Ca, Senior, Ba, Ra.
What is the boiling point elevation?
A colligative property, the increase in boiling point of a liquid as a solute is added.
What is an allotrope?
Different arrangements of atoms of a single element, e. G, diamond, and graphite are allotropes of carbon.
How can I carry out a chromatography experiment at home?
Chemistry principles encountered in this experiment: extraction, filtration, chromatography. Materials you'll need: rubbing alcohol, 250 ml, small jars with lids, baby food jars work well. Tree or plant leaves, 5 will do, coffee filters, pen containing hot water, kitchen utensils. The procedure: tear a few leaves up into small pieces, and place the pieces from each leaf into their own small jar. Add a small amount of rubbing alcohol to each, such that the leaves are just covered by the rubbing alcohol. Place the lids on the jars, and then place them in the hot water for 30 minutes. Replacing the water with fresh hot water if it cools. Swirl the alcohol in the jars every 5 to 10 minutes. By the end of 30 minutes, the pigments from the leaves will dissolve, and the alcohol solutions should appear colored. The alcohol serves as a solvent for extracting the pigments in the leaves. Cut long strips of coffee filter paper, remove the tops from the jars, and place one into each jar, with one end in the alcohol, and the other end outside the jar. The pigments will move up the paper different amounts, according to their size. You should be able to see the separation as different colored regions on the paper. Note that this process is a bit different from some of the separations we described in the modern chemical lab based on polarity or other chemical properties. Unlike chromatography on silica gel, the paper is not strongly polar and thus does not interact as strongly with the polar pigment molecules. Remove the strips of paper and allow them to dry. By comparing the relative distances the compounds traveled, technical term, retention factor, of the different compounds with one another, you should be able to identify whether the different leaves contain the same pigments. You can also try to make your alcohol solutions from other pigments, such as those in inks, foods, or drink. Try to design a hypothesis you can test using this experiment, such as whether or not the leaves of different plants contain the same pigments, or whether different markers or pens contain the same inks.
What is the boiling point?
Temperature for a given liquid at which its vapor pressure is equal to the external pressure acting on it.
Is ceviche really cooked by lime juice?
The results of cooking with heat and with acid are similar, but of course they are not exactly the same. Both heat and acid serve to denature proteins in food, which is a technical way of saying that the molecules change shape. With access to any number of shapes that it couldn't exist in beforehand. The molecule finds new ways to react both with itself and with other protein molecules. These recently liberated proteins quickly form a solid network, which is why fish gets firmer and whiter when you add lime juice. And it's the same reason that egg whites turn opaque and get harder upon cooking.
What is the antibonding orbital?
Orbitals in which the component atomic orbitals are out of phase, leading to repulsion or destabilization.
What is a bond angle?
The angle relating the orientation of two bonds connecting three atoms.
What is liquid smoke?
It's actually exactly what it sounds like, as crazy as that is. Smoke from a wood-burning fire is blown into condensers, which collect many of the volatile chemicals in smoke. This mixture is then diluted with water. It's used to cure bacon and flavor many other foods.
What makes a bowl microwave safe?
Unfortunately, the only definition is an empirical one. Containers that don't get hot in the microwave are microwave safe. Remember, or go look it up now in the world around us, that microwaves heat food by causing molecules with dipole moments to tumble back and forth. If the container has any such molecules, it'll get hot in the microwave. If any water has leached into your ceramic mug, it'll get hot in the microwave, regardless of whether the container gets hot on its own. The food you are heating up will get hot and transfer that heat to the bowl. So be careful when taking hot things out of the microwave.
Why would anyone add carbon monoxide to tuna?
Cutting a tuna fish exposes many muscle cells to oxygen, which slowly changes the bright red color of fresh tuna steaks to a darker brown. This is the result of iron-containing enzymes, myoglobin and hemoglobin, being oxidized from Fe2 to Fe3. Sushi lovers have come to understand that fresh raw tuna should be bright red and are skeptical of eating any brown-colored fish. The seafood industry figured out at some point that adding Co during the packaging step not only slows the rate of oxidation down, which increases shelf life, but also brightens the red color. It does this because Co binds more strongly to the Fe2 center than Fe3. The risk to consumers is not Co exposure here, but that you might be fooled into eating fish that isn't as fresh as you might otherwise think if you judge its freshness based on color.
What is an amplitude?
The height, or maximum displacement, of a wave.
What's in self-rising flour that makes it rise?
Baking powder and salt are added to flour to magically transform it into self-rising flour. Yeah, not so magical after all.
Why do shrimp change color when they're cooked?
Some, but not all shrimp, are grayish when they are raw, but turn pink once they're cooked. It makes sense to guess that this is because some chemical compound with a red color is being produced once you add heat. What's actually happening, though, is that the more intense pigments in the shrimp's shell are decomposing with heat, while the compound responsible for the red color is more stable. That red molecule is called astaxanthin. And it's not only found in shrimp shells but is also the reason that salmon meat is red. You'll probably be interested to know that there are a good number of chemistry experiments that you can perform right in your own home. While we can't teach every principle in this book with experiments that you can do with household items, we will do our best to illustrate some of the basic principles. Mostly those relevant to basic chemistry lab work, with items you may already have in your kitchen.
What is a bond length?
The distance separating two chemically bonded atoms.
What is an anode?
The electrode at which oxidation occurs.
What is a buffer?
A solution that tends to resist changes in pH upon addition of an acid or base.
What is a bonding orbital?
A molecular orbital that is more stable than the atomic orbitals that were combined to generate it.
What is an angstrom?
A unit of length used often to describe bond lengths, 1A equals 10 to 10 m.
What makes string cheese stringy?
In the United States, string cheese is usually mozzarella, sometimes with some cheddar thrown in. The production process takes melted cheese and stretches and folds it in a single direction. This stretching aligns the proteins in the cheese, making it possible to peel off long strings of it.
What is an alloy?
A mixture of metals, e.g., bronze, a mixture of zinc and copper.
What is anhydrous?
Without water.
What is a carbanion?
An anion in which a carbon atom bears a significant fraction of the negative charge.
What is a carbanion?
An anion in which a carbon atom bears a significant fraction of the negative charge.
What is carbocation?
A cation in which a carbon atom bears a significant fraction of the positive charge.
What is carbocation?
A cation in which a carbon atom bears a significant fraction of the positive charge.
What is a carbohydrate?
Organic compounds of carbon, hydrogen, and water. Typically with hydrogen and oxygen in a 2:1 ratio, respectively, these are often called sugars.
What is a carbohydrate?
Organic compounds of carbon, hydrogen, and water. Typically with hydrogen and oxygen in a 2:1 ratio, respectively, these are often called sugars.
What is a catalyst?
Any substance that increases the rate of a chemical reaction without being consumed by the reaction.
What is a catalyst?
Any substance that increases the rate of a chemical reaction without being consumed by the reaction.
What is a cathode?
Electrode where reduction occurs.
What is a cathode?
Electrode where reduction occurs.
What is a cation?
A positively charged ion.
What is a cation?
A positively charged ion.
What is Celsius?
Common temperature scale in which the melting and boiling points of water are defined to be 0 degrees Celsius and 100 degrees Celsius, respectively.
What is Celsius?
Common temperature scale in which the melting and boiling points of water are defined to be 0 degrees Celsius and 100 degrees Celsius, respectively.
What is a ceramic?
An inorganic crystalline solid typically prepared by heating.
What is a ceramic?
An inorganic crystalline solid typically prepared by heating.
What is a chalcogen?
A group 16 element, oxygen, sulfur, selenium, tellurium, polonium, or livermorium.
What is a chalcogen?
A group 16 element, oxygen, sulfur, selenium, tellurium, polonium, or livermorium.
What is the Charles's law?
A law stating that the volume and temperature of a gas are directly proportional.
What is the Charles's law?
A law stating that the volume and temperature of a gas are directly proportional.
What is the chelation?
Binding of a ligand to a metal atom through 2 or more positions.
What is the chelation?
Binding of a ligand to a metal atom through 2 or more positions.
What is a chemical bond?
Sharing of electrons between 2 or more atoms.
What is a chemical bond?
Sharing of electrons between 2 or more atoms.
What is an atomic weight?
The average mass of an atom of a given element.
How can I make black snake fireworks from items around my house?
Note, this experiment involves fire and flammable materials, so adult supervision is required. Also, check your local laws before attempting this experiment. Chemistry principles encountered in this experiment. Chemical reactions, combustion reactions, materials you'll need: sand, about 2 cups, lighter fluid, a small bottle of about 100 milliliters. Baking soda, 1 tablespoon, sugar, 4 tablespoons. Cup or bowl: an outdoor location where you can light the black snake firework safely without damaging anything. The procedure: in a cup or bowl, mix 4 tablespoons of sugar with 1 tablespoon of baking soda. Use the sand to form a pile, in your chosen safe outdoor location. And then create a depression in the middle of the sand. This depression is where you will ignite the black snake firework. Pour a small amount of lighter fluid onto the sand to wet it. Try this experiment first with a very small amount of lighter fluid, and, if necessary, repeat the experiment with incrementally larger amounts. It's better to start too small than too big. Pour your mixture of sugar and baking soda into the wetted depression in the sand. You don't have to use it all at once. Feel free to experiment with different quantities of the baking soda and sugar mixture. Carefully ignite the lighter fluid with a match and stand back. You should see the mixture create long snakes of black ash. The burning sugar and baking soda form sodium carbonate, water vapor, and carbon dioxide gas. The ash in the snake is composed of carbonate and burnt carbon.
How can I study the effects of acids and bases on sliced fruit getting old and turning brown?
Chemistry principles encountered in this experiment: acids and bases biochemical/enzymatic reactions materials you'll need. An apple, other fruits like bananas, pears, or peaches will also work. 5 clear plastic cups vinegar, lemon juice, baking soda, water, milk of magnesia, measuring cups. The procedure: prepare aqueous solutions of milk of magnesia and baking soda. The amount of water you use isn't particularly important. Feel free to test various concentrations if you'd like. The key aspects are that the baking soda dissolves completely and that the milk of magnesia solution becomes less viscous or thick. Slice your apple, or other fruit of choice, into 5 pieces. If you have decided to test multiple concentrations of baking soda or milk of magnesia solutions, adjust the number of fruit slices accordingly. Label the cups as follows: vinegar, lemon juice, baking soda solution, milk of magnesia solution, and pure water. Place 1 slice of fruit in each cup. Add about degree of a cup of the appropriate solution to each of the cups you have labeled. The fruit should not be completely submerged in the solutions, but make sure each slice of fruit gets completely coated with the solution. The vinegar and lemon juice solutions serve as acidic solutions, of acetic and citric acids, respectively. The baking soda and milk of magnesia solutions serve as basic solutions of sodium bicarbonate and magnesium hydroxide, respectively, while the water serves as a neutral control solution. Write down your observations regarding the physical appearance of each piece of fruit at this time. If you have a camera handy, it might be useful to take a picture of your fruit samples for comparison to the final results. Allow the fruit to sit for 1 day, and then come back and record your observations again. If you took a picture on the first day, you can compare the current appearance of the fruits to your photograph. Apples and fruits turn brown when an enzyme called tyrosinase, refer back to chemistry in the kitchen, carries out a chemical reaction in the presence of oxygen and phenol-containing compounds.
What is Celsius?
Common temperature scale in which the melting and boiling points of water are defined to be 0 degrees Celsius and 100 degrees Celsius, respectively.
What is a cation?
A positively charged ion.
What is beta particle?
An electron created during nuclear decay reactions.
What is an atomic orbital?
An equation that describes the probability of finding an electron around a nucleus.
What is the Avogadro's number?
The number of particles in 1 mole, 6.022 x 1023.
What is a cathode?
Electrode where reduction occurs.
What is an atomic number?
Number of protons in an atom.
What is a catalyst?
Any substance that increases the rate of a chemical reaction without being consumed by the reaction.
What is a barometer?
An instrument used to measure pressure.
What is a base?
A compound that accepts hydrogen ions, Brønsted-Lowry acid. Has a pair of available electrons, Lewis, or releases hydroxide ions in solution, Arrhenius.
How can I make a volcano from vinegar and baking soda?
Chemistry principles encountered in this experiment, chemical reactions, gases, materials you'll need. Vinegar, baking soda, 2 tablespoons, large bowl, baking pan flour, 6 cups, cooking oil, 4 tablespoons. Salt, 2 cups, plastic bottle, dishwashing soap, red or orange food coloring, or any color, really. Water. The procedure. This is a classic chemistry experiment that you might have done before in school. In a large bowl, first mix 6 cups of flour, 2 cups of salt, 4 tablespoons of cooking oil, and 2 cups of water. Mix these ingredients until they are firm. These ingredients are not involved in the chemical reaction that will make your volcano erupt, but rather this mixture will serve as the rock that forms the structure of your volcano. Place the plastic bottle standing vertically in the pan. Use your hands to shape the rock material from the first step into a cone shape around the top of the bottle. Be careful not to cover the top of the bottle. Fill the bottle most of the way with water, leaving enough space to add a few ounces of baking soda and vinegar. Add a few drops of dishwashing soap to the bottle. This is not part of the chemical reaction that will take place inside the bottle, but bubbles from the soap will help to catch the gas evolved during the reaction between the vinegar and baking soda. Add 2 tablespoons of baking soda into the bottle. Finally, slowly or quickly, if you want a really crazy volcano. Add vinegar to the bottle, and prepare to witness the eruption. Be careful though, you should avoid getting this mixture in your eyes or anyone else's, and this combination can make a spectacular mess in your kitchen. The chemical reaction takes place between the baking soda, sodium bicarbonate, or NaHCO3, and vinegar. Dilute acetic acid, or CH3CO2H, to release carbon dioxide gas, which is what causes the volcano to erupt. The relevant chemical equation is NaHCO3 plus CH3COOH CH3COONA and CO2 plus H2O.
What is a chemical bond?
Sharing of electrons between two or more atoms.
What is carbocation?
A cation in which a carbon atom bears a significant fraction of the positive charge.
What is the Charles's law?
A law stating that the volume and temperature of a gas are directly proportional.
How can I make invisible ink?
Chemistry principles encountered in this experiment. Evaporation combustion reactions acid/base reactions materials you'll need, cotton swab or paintbrush heat source. Can be a light bulb, measuring cup paper baking soda water grape juice, optional, the procedure. To prepare the ink, just mix equal volumes of water and baking soda and stir well. Take a cotton swab, paintbrush, toothpick, or something similar, and write a message on a piece of white paper using the water and baking soda mixture you have prepared. Allow the ink time to dry. The water will soak into the paper and eventually evaporate. But the baking soda will not evaporate and it will be left behind. To read your invisible message, there are a couple of options. One is that you can hold the paper to a heat source, such as a light bulb or gentle flame. Don't burn the paper. This should cause the baking soda on the paper to turn brown, revealing your message. The baking soda burns faster than the paper, which is why it turns brown before the paper does. Another option is to spread purple grape juice over the paper. You can use a paintbrush to do this. The message should appear in a different color/shade compared to the rest of the paper. This works because an acid in the grape juice reacts with the sodium bicarbonate that you used to write your message.
What is a band gap?
the energy range separating the top of the valence band and the bottom of the conduction band in a semiconductor.
What is an atom?
Smallest unit of a chemical element.
What is an atomic radius?
Half the distance between nuclei of the same element.
What is a chalcogen?
A group 16 element, oxygen, sulfur, selenium, tellurium, polonium, or livermorium.
What is the chelation?
Binding of a ligand to a metal atom through 2 or more positions.
What is a ceramic?
An inorganic crystalline solid typically prepared by heating.
Do you notice a change in the part that you dipped into the solution?
Place the remaining pennies into the solution. You will likely notice a visible reaction as the pennies are placed in the solution. The reason pennies eventually begin to appear dull is that the copper surface reacts with oxygen in the air to create a layer of copper oxide. In this experiment, the vinegar and salt will react with the copper oxide and remove it, which will leave a layer of the original shiny copper exposed on the surface. Allow the pennies to remain in the solution for several minutes. If necessary, try to move the coins around so as to expose both sides of each coin to the solution. If possible, flip the coins over after a couple of minutes. Drain the solution and rinse the coins with clean water. They should now look clean and shiny.
How can I observe the effects of electrostatic forces using household objects?
Chemistry principles encountered in this experiment: electric charge, electrostatic forces. Materials you'll need: nylon hair comb, or a latex balloon, a water faucet. The procedure: comb your hair with a nylon comb. If you don't have a comb, you can also rub your head with an inflated latex balloon instead. As you rub the comb or balloon to your head, it builds up an electric charge on the object due to the movement of electrons between the object and your head. Go to the faucet and turn it on so that a narrow stream of water flows out. Try to make the stream as thin as possible, while still maintaining a steady, smooth flow of water. With the water running, move the comb or balloon close to the stream of water. But be careful not to actually let the comb or balloon touch the water. As it gets close, the stream of water should be deflected toward the comb or balloon. This is because the charge in the object, comb or balloon, induces an opposite charge in the nearby water. And the object and water then experience an attractive electrostatic interaction, opposites attract. You can experiment with how the amount of deflection varies with the size of the stream of water from the faucet. You can also compare the ability of various objects, different combs, balloons, or different objects altogether, or vary the amount of time you rub the object in your hair.
How can I test the hardness of objects around my house?
Chemistry principles encountered in this experiment, hardness materials, science materials you'll need. Collect several materials of known hardness, examples include, numbers are based on the Mohs scale. Fingernail, 2.5, penny, 3, glass, typically 5.5 to 6.5, quartz, 7, steel, typically 6.5 to 7.5, sapphire. 9. You can also look for additional items from the list provided at the end of this experiment. Or search online for additional objects that have been ranked on Mohs scale of hardness. Of course, you can also choose item of unknown hardness and determine their hardness in this experiment. The procedure: locate a specimen whose hardness you want to test. Note that you will be attempting to scratch the object. So don't choose anything too valuable or anything you don't want scratched. Select an object of known hardness from those you gathered. And try to scratch the surface of your sample by pressing it with the tip or edge of the object of known hardness. For example, let's say you wanted to test a piece of wood. You could try to scratch it with a piece of quartz by pressing the edge of the quartz into the wood. Inspect your sample to see if you have made a scratch in it. You may need to feel the surface of the object with your finger to check thoroughly. If your object was softer than the sample of known hardness, there will be a scratch. If it was harder, then there will not be a scratch. Repeat the test a couple of times to verify the result. Continue performing the scratch test with various objects of known hardness, until you find two adjacent objects on your list, such as a fingernail, 2.5, and a penny, 3, in between which the hardness of your sample rests. You will know you've found this pair of objects on your list when the harder object of the pair does scratch your sample, while the softer one does not. Once you have found this place on the list, you can assert that the hardness of your unknown must lie between that of the two objects of known hardness on the list. For example, if a penny, 3, scratches your object, and a fingernail, 2.5, does not, your object must have a hardness between 2.5 and 3. Additional Mohs hardness rankings: talc, 1, gypsum, 2, calcite, 3, fluorite, 4, platinum or iron, 4.5, apatite, 5, orthoclase, 6, quartz, 7, garnet, 7. Hardened steel: topaz, emerald, 8, corundum, 9, diamond, 10.
How can I make slime?
Chemistry principles encountered in this experiment. Hydrogen bonding synthesis polymer chemistry cross-linking materials you'll need: water Elmer's glue, about 4 ounces. Or 120 ml, borax powder, 4 to 5 tablespoons, bowl measuring cup small jar. Doesn't need to have a cover, spoon or stirring device. Food coloring, optional. The procedure: pour about 4 ounces of white glue into the jar. The glue contains several components, including the polymers polyvinyl acetate and polyvinyl alcohol. See polymer chemistry. Polyvinyl acetate contains oxygen atoms that can serve as hydrogen bond acceptors, and polyvinyl alcohol contains hydroxyl groups that can serve as either hydrogen bond donors or acceptors. Add 1/2 cup, 4 ounces or 120 ml, of water, and stir it in until it mixes with the glue. Note that there is already some water in the glue, and we are just adding more. Optional: add food coloring to the mixture to give your slime some color. In the bowl, mix 1 cup, 8 ounces or 240 ml, of water with 4 or 5 tablespoons of the borax powder. Stir this well. Here we are preparing a solution of borax so that we can add it to the mixture of glue and water in a more uniform fashion. While mixing, slowly add the glue and water mixture to the solution of borax. As you mix, you should observe the slime forming. Pick it up with your hands and knead it until it seems fairly dry. There will still be extra water left behind in the bowl. That's nothing to worry about. The borax serves to cross-link the polymers by forming hydrogen bonds with the oxygen atoms of the polymers in the glue. These interactions can readily rearrange to form new hydrogen bond donor acceptor pairs with different oxygen and hydrogen atoms, which is what makes the glue so stretchy and readily deformed. When you are done with it, you can store the slime in a plastic bag in the refrigerator.
What is the azeotrope?
A mixture that does not change composition during distillation.
How can I make hot ice? Sodium acetate.
Chemistry principles encountered in this experiment. Chemical reactions: solubility, crystallization and recrystallization, colligative properties. Materials you'll need: pan with cover, microwave or stovetop, vinegar, 1 liter, baking soda, 4 tablespoons, Dish the procedure. Pour the vinegar into a pan, and very slowly, a little bit at a time, add the baking soda. As you may already know, this reaction will produce large amounts of bubbles. Carbon dioxide gas, so you'll need to add this very slowly. This reaction will produce a solution of sodium acetate in water. Sodium acetate is produced according to the chemical equation Na plus HCO3 plus CH3COOH CH3 Co Na plus H2O and CO2. Bring the solution to a boil. Allow the solution to continue to boil until a skin or film begins to form on the surface of the solution. This will require heating for a significant amount of time, perhaps up to an hour, until a large fraction of the water from the vinegar has evaporated. Our goal here is to form a very concentrated hot solution of sodium acetate. You'll recall from our discussion of colligative properties that the solubility of a solute is higher at higher temperatures. As we reduce the volume of the water, the sodium acetate will not evaporate, and we will be left with a concentrated solution at high temperature. When you notice a film start to form on the surface, remove the pan from the heat, and cover it to prevent further evaporation. Place it on the countertop or in the refrigerator to cool. If you see any crystals begin to form, add a small amount of additional vinegar, or if you are out of vinegar, use water and stir the solution so that they dissolve. You now have a supercooled solution of sodium acetate that can crystallize out of solution readily if a crystallization nucleus is present. You can now slowly pour the first few drops of the cooled solution onto a dish, and it should begin to crystallize rapidly. If it doesn't, try dragging a fork or knife along the dish to make a tiny scratch. Or give the liquid a moment to evaporate a little so that the sodium acetate begins to crystallize before you begin to pour. As you continue to pour, the liquid should continue to crystallize as it contacts the crystals already formed on the dish. This is similar in spirit to how purification takes place during a recrystallization. See the modern chemical lab. If you feel the crystals, they will be warm to the touch. Since the crystallization is an exothermic process, it gives off heat. This is why it's called hot ice. But now you know it isn't really ice, it's sodium acetate, and you know how to make it.
What is a bimolecular reaction?
A reaction that involves two molecules in the rate-determining transition state.
What is a carbanion?
An anion in which a carbon atom bears a significant fraction of the negative charge.
How can I show my friends a magic trick using pepper?
Chemistry principles encountered in this experiment Polarity surface tension materials you'll need: a shaker or small packet of black pepper dishwashing soap, a few drops. Bowl water, a bowl full. The procedure: begin by filling the bowl with water. Then pour black pepper onto the water to form a thin layer of pepper across its surface. As a control experiment, try dipping your finger below the surface of the water. Nothing too interesting should happen at this time. Now rub a small amount of dishwashing soap on your finger and dip it in the water again. This time, you should see the pepper move away from your finger and toward the edges of the bowl. The nonpolar soap molecules don't want to dissolve beneath the surface of the water, and thus they spread across the surface of the water quickly, which lowers its surface tension. Whereas water typically bulges a bit above its surface due to its relatively high surface tension. The water spreads out when its surface tension is lowered. This causes the water to spread out as the soap moves over it, and the pepper is carried away from your finger in the process. Now that you understand the basics of this trick, you can perform it for your friends. Ask a friend to dip their finger in the water and to try to concentrate on trying to make the pepper move away from their finger. When they cannot make it happen, you can step in and use your already soapy finger to easily move the pepper away.
What is a carbohydrate?
Organic compounds of carbon, hydrogen, and water. Typically with hydrogen and oxygen in a 2:1 ratio, respectively, these are often called sugars.
How can I observe layers of immiscible liquids?
Chemistry principles encountered in this experiment: density, miscibility, polarity, materials you'll need asterisk. Honey, pancake syrup, liquid dish soap, water, vegetable or cooking oil, rubbing. Alcohol, lamp oil, a tall glass of water or other container, optional, food coloring to improve visibility asterisk note. For this experiment, it is not necessary to have every material listed. The procedure: pour the densest liquid into the glass first. Note that the liquids above are listed from most dense to least dense. Try to avoid letting the liquid run down the sides of the glass. Gently pour the second liquid on top of the first. One way to pour it a little more slowly is to pour the liquid over another object such as a butter knife or the backside of a spoon. Allow each layer of liquid to settle for at least a few seconds before adding the next liquid. You'll notice that, instead of mixing, the liquids tend to stay in separate layers. The reason for this is that they are immiscible, which means that it is more thermodynamically favorable for the liquids to stay separated in layers and to form an interface than it is for them to mix together. Whether or not two liquids will be miscible is dictated by the details of the entropic and enthalpic factors associated with the mixing or separation of the two liquids in question. This is often directly related to whether or not the compounds have similar polarity. For example, we know water is a very polar substance, while vegetable oil is composed of primarily long, nonpolar hydrocarbon chains. These do not interact favorably with one another, and prefer to stay in separate layers. Continue pouring the third, fourth, etc. liquids on top of each other in order of decreasing density. You can just follow order of your liquids in the list above. As you pour in the successive liquids, they should continue to form separate layers. The densest liquids are affected the most by gravity, so these tend to stay below the less dense liquids. These liquids are not miscible, so they do not mix together to form a single solution. In truth, if you wait long enough, some of these liquids will mix together. But it will take a while. That's it. You should now see a series of separate liquid layers in your container.
How can I use chemistry to make dull pennies shiny?
Chemistry principles encountered in this experiment: surface chemistry, oxidation reactions, materials you'll need. A handful of dull pennies, 10 will do, 1 teaspoon table salt, sodium chloride. 1/4 cup white vinegar, acetic acid solution, a small, non-metallic bowl, water, paper towels or napkins. The procedure: pour 1/4 of a cup of vinegar and 1 teaspoon of table salt into the bowl. Stir the mixture until the salt is completely dissolved. Try first dipping 1 penny into the solution for about 15 seconds and remove it.
What is a chemical change?
A process that alters the arrangement of atoms in a substance.
What is a chemical change?
A process that alters the arrangement of atoms in a substance.
What is a chemiluminescence?
Emission of light resulting from a chemical reaction.
What is a chemiluminescence?
Emission of light resulting from a chemical reaction.
What is a chiral center?
An atom whose arrangement of substituents is non-superimposable with its mirror image.
What is a chiral center?
An atom whose arrangement of substituents is non-superimposable with its mirror image.
What is a chirality?
A geometric property of a molecule whose mirror image is non-superimposable with the original molecule.
What is a chirality?
A geometric property of a molecule whose mirror image is non-superimposable with the original molecule.